Good evening to you all. My name is Chetan Conikee and I have a high density of slides and 20 minutes to get past everything. So I'm going to speed up and feel free to interrupt, or perhaps we can take a Q&A after we wrap. My name is Chetan Conikee and I'm the founder and CTO of a venture-backed security company called Shiftleft that was founded by executives of FireEye, Palantir, and Google. So the topic of today is to focus on identifying how microservices could potentially leak critical data. So I'm going to start with this slide where, it's again, I might be preaching to the choir on this, which is your application is your business, but data is the lifeblood of the application, meaning every application that you code and deploy in production is dealing with data. It's either creating, transforming, or deleting data, which is your customer data in some way, shape, or form. A very quick stat, 2.5 quintillion data bytes are being created every day. And as a consequence of this creation, approximately 9 billion data elements or records are being breached. Now, the consequence of the breach is either data exfiltration, which is very similar to what happened with Equifax as a consequence of them using a vulnerable version of struts. The other is an engineer in your company inadvertently leaking data to third-party vendors that you procured and use. This is a very quick representation of your stack, your production stack, again oversimplified to a certain extent. But the point that I want to draw with this slide is everything starts with a simple microservice fleet communicating with your databases where you're persisting your customer data. And then lo and behold, when you achieve product market fit, your salesperson shows up and implements Salesforce, and he wants all the data to target and identify your customers to upsell. And then your marketing person shows up and he hooks up Mixpanel because he wants to track how your users are consuming and using your product. The consequence of this is, as you hook and integrate these products, you begin to actually send data. Data that you're not aware is critical from a perspective of compliance. Now, if I have to ask you application stewards for these very 4 critical questions from the perspective of data, which is, can you identify what is sensitive from your business line perspective? And can you identify and understand the lineage and provenance of that data? Because often, no one parses the legal minutia of perhaps a PCI DSS or a GDPR or perhaps a California Act. But most of these compliances speak about the fact that your customers own their data and it is your job to protect their data and give them visibility into where else it is going. Typical current approaches is, often we react to a situation, meaning that we conduct an audit, and if we are deemed as non-compliant, the first thing we do is quickly implement a WAF. Now, if you get your first customer who's a Fortune 500 customer who says that, are you secure? And they send you that crazy long Excel spreadsheet, you're gonna either answer maybe or yes and run to implement a WAF, a CASB, or a DLP. To expand on these acronyms, DLP is Data Leak Prevention, CASB is Cloud Access Security Broker, and WAF is Web Application Firewall. Often these are installed at the perimeter with the assumption that if you put it out there, you're pretty much CYA or covering your ass, if I have to expand that. Now, as you implement this solutions at the gateway, it is acting as a proxy between your customer and your microservices. And then you need this human who has to manage policies and rules upon these systems and thereafter react to incidents and responses. Often the focus is vulnerability detection or perhaps threat detection, but as a consequence of lack thereof of compliance, you make that as a function as well. So let's quickly take a gander at the evolution of these systems. Back perhaps 2 decades ago, these systems used keyword matching, meaning, large compliance and regulation bodies had a bunch of clauses, but they all permeate towards certain keywords that are considered as critical. And those keywords are finance, which is routing number, social security number, etc. And over the wire, these systems were trying to do basic string matching to identify if those elements are leaking, meaning they're examining the value, they're almost man-in-the-middling your traffic or sharing the cert, and thereafter examining if that data is exiting the crevices of your application. The issue with such systems is they completely lack context, meaning if you have a fleet of microservices on the other end, and if it's just doing basic string matching based on baseline dictionaries, it does not have any understanding of what is leaving or what is sensitive from your business line perspective. Now, as they evolved, the next affirmative evolution was pattern matching, where you essentially have a series of regular expressions. You're again examining on the wire, and you're matching to see if a certain expression looks like a credit card number, or perhaps a AWS key or an Azure key. The consequence of this is everything looks like a SHA-1 hash code. And if so, it's hard to identify whether that is an unique user ID or perhaps an AWS key or an Azure key. So for this, you have to train your models. That's where you bring statistics and throw that label of AI and say that you have an effective system that can quantify that this is a key and not a unique user ID. As a consequence, too many false positives, hard to identify what you're dealing with. Now, an overlay over this is again applying certain statistical principles, which is very similar to naive Bayes filtering, which is applying probabilistic data structures and identifying what is not critical and what is critical as you sense on the wire. So on summary, even though it's evolved to applying statistics, pattern matching, yet it is operating at the perimeter and has absolutely no understanding of what your applications are and what is your business line. And the other issue is it's broken at the speed of DevOps. I presume all of us here are doing some degree of DevOps, which is we are deploying our product and features at high velocity, which is multiple builds a day. So if you're deploying multiple builds a day, your statistical model does not have time to stabilize and provide true positives. So let's flip the coin and examine an inside-out approach. DevOps is nothing but from the far left, your engineers write code, check code into an SCM or source code management system, and then you have webhooks that inform your build systems. So the build and packaging of your artifacts happen in the middle, and thereafter, based on certain decisioning parameters, you deploy that software in production. Note, all of this is happening multiple times a day and a week, or perhaps a month. So if you have to deconstruct your application, almost over 80% of your application is comprised of open source, deployed on a web framework, running on a open runtime machine or a virtual machine. If you're examining the constitution of your application in its entirety, it almost looks like a graph. That's how your compilers see it. Because when you compile code written in Golang, Java, Python, or any language, the compiler is taking multiple passes. The first pass is parsing and lexing based on the grammar of the language. Thereafter, optimizing your control flows, and eventually identifying program dependence flow. So these are 3 steps that your compilers take to analyze and optimize your code. In the world of security, if this graph is examined in its entirety, a typical security analyst is examining what they call as taint propagation. Because often when attackers attack your application, they are sensing where your sources are at, because typical web applications have web routes, that's your sources. And then you have flows, function flows that are being triggered to serve your customers' business needs, communicating with various sinks like databases, other microservices, or perhaps the file system. Now, between the sources and the sinks are validation and transform functions. Validation is where you're validating your input, because from the world of security, every input is untrusted. So you're validating to check whether a particular attacker is applying some degree of an exploit pattern. Transforms are at the edges or the crevices of the sinks. When you write to a database, when you write to a logging vendor or a third-party SaaS solution, you conduct some degree of encoding, obfuscating, or encryption. So from a compliance standpoint, that's what they care about. First of all, what is sensitive? Are you doing a good job at obfuscating and encrypting those elements that are deemed sensitive before it exits your application into the world of your third-party vendors? So this graph is really hard to parse because, the density of code that we write is significantly complex. So from the security standpoint, they created a particular standard called as the entry-exit framework. It's a framework that simplifies the representation of your code. It almost looks like a Docker file, but it describes how your code is behaving when operational. So let us quickly identify how can we classify sensitive data from inside out. Now this, for sake of simplicity, I'm going to use a construct or a typical code snippet from a Java program. It's an object-oriented program. You define classes, and you have attributes, and then you have accessors and mutators, which are getters and setters. These classes represent your business objects with fields. Now when you examine the semantics, rather than looking at values, if you have this at your dispense, you can apply natural language processing and examine the semantics of how the class is described. Because instances of these classes are created in business workflows, your customer data is fitted into those instances, and then data is moved back and forth. So if you take a quick look at this example, we have a class patient, and we have phone, address, social security number, etc. So when you apply natural language processing, what we can essentially do is score this object from a sensitivity standpoint associated to your business line. Now as this object is instantiated, meaning you're creating an instance of this class in a workflow. Now this is a quick example of a typical HTTP GET workflow. It goes ahead and accepts the input from the request and then deserializes that input and fits it into that instance of that object being created. Now that object comes to life, it represents your customer, and somewhere in the middle you have a log.debug statement. In certain cases, engineers want complete traceability and visibility. So as a consequence, they might inadvertently send that entire data to your log file. And then your rsyslog daemon picks it up and sends it to Splunk. And thereafter, your Splunk admin has complete visibility into all sensitive data of your customers. Case in point, this is exactly what happened with Twitter not too long ago. One of the engineers placed a log.debug before they applied the encryption util, and that data got picked up by the daemon, sent to a third-party company that was managing their security and traceability, which is why all of us received that email to change our passwords. So as we apply the input-output flow, we can very quickly treat this as a graph and identify where your data might be leaking at by applying semantics rather than just patterns and everything that you can think of as I spoke of earlier. So with this, for the most part, you can very easily answer these 3 questions, or perhaps 4 questions, I'm sorry. Where is the data originating? Because that data had a specification, which is your class. And when you create that data, either in locality space in a function or in global space, you understand its lineage and provenance. And thereafter, as data flows from application and hops into other applications as they communicate with microservices, you understand how it flows, where else is it flowing. So from a GDPR or California Act perspective, if a customer wants his data to be purged, just merely purging in your databases is not going to solve that problem. So having lineage and provenance means you have an understanding of where else to go to purge, or what you shouldn't be doing for the most part. How can the solution be relevant in the world of DevOps? We spoke of code, we spoke of a graph that can be extracted, that has all the semantics, and thereafter, how can this be observed in production so that it is quantified with proof of leakage? So the system that we speak of should be capable of adapting into the world of DevOps, meaning in a matter of minutes, as you check in your code, the graph should be created. Thereafter, the semantics and the information we spoke of should be extracted. That becomes a policy that is fed in runtime to observe and identify if this leak is really happening, which is your proof of leak. Note, with this approach, you have no humans. The humans are augmenting certain dictionaries, meaning there is a baselining, but after that, they don't interfere with the system. If this is continuous, it makes it relevant and easy to understand your compliance position, and your answers are not vague, especially when you're going through a compliance audit. Thank you. Any questions? Please.
So could you just go into a little bit more detail on how the Twitter compromise happened? It was not encrypting.
So Twitter was essentially salting, and they applied bcrypt to encrypt their passwords before they persisted their passwords in their databases. And alongside, there were a certain set of log statements. So everything critical in that path was being redacted. During a triage incident, one of their engineers had inadvertently placed a log statement, a log.debug. And someone forgot to enforce or disable debug log in production. So as a consequence, that data got persisted into the logger, which is a log file, and the rsyslog daemon picked it up and sent it to the third-party logging vendor. So as a consequence, that data was available in clear text to the SOC admins, which is why when they were conducting a GDPR audit, they realized this. This was not a breach, by the way. I presume it was KPMG or one of the firms that conducted a detailed audit. And that audit essentially involved looking at their code base and identifying where else is data moving. Did I answer your question? Thanks. Yes, please.
So, we saw the problem, right? And what are all the solutions possible for this to solve this? So, as of, yes, there was a log, and there is a debug, and there is a graphing, as a DevOps, where are all the places to look for, and how do I handle it effectively?
Without sounding like a product pitch, we essentially built this product to solve the problem, actually. I don't mean to insert the product, but our intention was this, that it's relatively hard for someone to understand evolution of code, because code gets exponentially complex as you evolve year to year and as you add more engineers to your staff. So we built a system that can identify, first of all, convert code to a graph in minutes, and then primarily extract vulnerabilities and correlate that to threats. That's the primary function of our solution, which is Shiftleft. as a consequence, we created a compliant solution as well, because some of the customers asked for it.
So essentially, what you're doing is you're examining like plain text files with natural language processing to see if there's things like social security numbers or other things that would indicate a security issue is happening. Is that essentially correct?
It's your code actually. It's not plain text file. You know, as you write code in any language,
Right.
we map it to a unified representation. And that representation actually looks like a graph, a typical social network graph. Rather than having humans connected, you have functions connected,
Right.
and then you have data that is exchanging hands between functions. So this technology was a part of a PhD dissertation thesis. It was called as Code Property Graph, invented by our chief scientist. And there are reference implementations of this technology in Microsoft. It's the Roslyn compiler on Microsoft is based on our technology. And Google's code search engine is also inspired based on our technology.
Roslyn,
Roslyn. I'm sorry, you had a question? I think it was you.
Yeah, I was thinking back to the graph that you showed where you sort of got the CI/CD system that's enabling the scanning of the code, and then the code goes to production, and then the validation happens. Is it at all possible, given that it looks like the validation being in production is after the risky code is in production?
Not necessarily. Actually, you can preemptively interject before. If you have a decisioning system, you can make that decision not to let that code be deployed in production.
Okay.
But often there's high cognitive load because, you know, most of the time none of the systems are accurate, which is why there's a high degree of false positives, right? So from a production standpoint, you're getting the proof of exploit or the proof of leak, which helps you prioritize the issue.
Is it possible, based on the graph, to sort of assign a risk to the results and allow lower risk code out while preventing high risk code from going out?
Absolutely.
Or is it a little too fuzzy?
It's mostly heuristical, but as your consumers begin to interact with your application, it becomes deterministic. Because you know, the graph can only, when you have a system that is measuring code which is non-operational, you don't understand all the permutations and combinations of values that it can subject to your application. Because attackers mostly are spraying and praying. They're like script kiddies using a burp suite or zap, trying to hit your application and figuring out ways to exploit it. Good. Thank you.